Hi, I'm Chao-Tsung Huang from National Tsinghua University, Taiwan. The title of this paper is RingCNN, Exploiting Algebraically-Sparse Ring Tensors for Energy-Efficient CNN-based Computational Imaging. This is my outline of this presentation. I will first talk about the opportunity and challenge of applying CNN-based computational imaging on portable imaging and display devices. Then I will quickly review the background information of sparsity techniques and summarize our motivation. Then I will introduce our proposed RingCNN framework and how we implement it into an accelerator architecture. Finally, we will use extensive model and design evaluation to show the effectiveness of our idea. As we know, CNN-based computational imaging can bring unprecedented image quality for traditional image processing applications, such as denoising and super resolution. It can also bring some applications which are imaginable before. For example, style transfer. We can turn this photo into Picasso painting style. What's even better is that we can have unlimited upgrade scheme. It means we can update or upgrade any trainable algorithm anytime and anywhere. However, this opportunity comes with a difficult design challenge on edge devices. This is because CNN-based computational imaging requires to generate high throughput and fine textured feature maps. And this leads to an intensive demand of computation. For example, for the advanced CNN denoiser FFDNet, if we want to use it to generate videos with 4K Ultra HD resolution at 30 frames per second, the computation demand will be up to 106 tera operations per second. And this will certainly lead to serious issues on battery and heat. Since sparsity seems a reasonable technique to address this issue, I will quickly review the background and summarize our motivation. Here are two well-explored approaches on sparsity. The first one is natural sparsity. It exploits weight and/or feature sparsity on pre-trained models, such as weight pruning or visual gating. For example, for the dense matrix here, we can remove some unnecessary weights to reduce storage or computation. And the second one is low-rank sparsity. It suggests to decompose or reconstruct models or matrices into low-rank alternatives. For example, this is a rank 1 approximation for this dense matrix. Then here are two less explored approaches. The full-rank sparsity simplifies matrix vector multiplication with full-rank transforms like here. It preprocesses the data using this transform and applies component-wise product here and then reconstruct the data. For the previous work through CNN, it applies Fourier transform, and for AdaNet, it applies Hadamard transform. The last one is algebraic sparsity. It applies n-tuple ring algebra to construct models, such as using complex number or quaternion. This is an example for this 4x4 real matrix. We can use this 2x2 complex matrix for approximation. However, the main issue of those previous approaches is that they are not optimized for computational imaging. For natural sparsity, it can give good image quality, but the regularity is not good, so the hardware efficiency is not ideal. For the low-rank sparsity, it has a better regularity, but with some experiments we find that the image degradation will be very serious when generating local details for computational imaging. And we have a quality regularity dilemma here. And for the algebraic and full rank sparsity, they are very regular, but we only have limited variants to choose from previous work. So our motivation is simple. Is there any way to improve regularity and quality simultaneously for computational imaging? Our solution here is to exploit algebraic sparsity. It is because it can essentially provide local sparsity and global regularity to facilitate efficient architecture design. Also, based on the analytical properties of algebra, we can build a unified framework called RingCNN to jointly optimize quality and efficiency. Now I will introduce our proposed RingCNN framework with ring algebra. But before getting into the details, I would like to use this toy example to show how complexity can be saved. For this small system with 2 output channels and 4 input channels, we need 2x4 matrix for the weight parameters. But if we use complex number to construct this system, we only need 1 complex number for the output and 2 complex numbers for the input. So we only need this 1x2 complex matrix for the weight parameters. For the matrix G here, the original degrees of freedom is 4. By using complex number, it can be reduced to 2. So we can reduce weight storage by 50%. As for complexity, for this complex multiplication, there is a famous FAST algorithm. It has 3 steps. The first one is filter and data transform, and then apply component-wise product in the transform domain, and finally reconstruct the data. Here, we only need 3 multiplications instead of 4, so the complexity saving is 25%. Based on this idea, we propose to construct CNN models using ring algebra. A ring algebra is a set R of n tuples with 2 fundamental operators. The first one is addition. Here we simply use the component-wise addition. And the other operator is multiplication, and it is more complicated. Here we assume it has a bilinear form, like here, which can enable fast algorithm. By factorizing the indexing tensor, we can have the filter, data, and reconstruction transforms. So here we can have a quick summary. By using the n-tuple ring algebra, we can always have n times weight saving. But for complexity saving, it will depend on our definition of ring multiplication. In addition to construct neural networks, we need to define another function, nonlinearity. And a common choice is to use component-wise rule. Besides the algebras we know, such as complex number, quaternion, and group convolution, we want to do a more extensive comparison for different ring algebras. So we do a systematic search for ring multiplication based on the following three assumptions: exclusive distribution from input to output, the commutativity of ring multiplication, and minimum generic tensor rank. These assumptions can lead to high capacity, associativity, and low complexity, respectively. Our search results include full-rank rings which are similar to RingCNN and AdaNet, and we also find 4 new variants for n equals to 4. However, complexity 7 depends not only on the number of real multiplications, but also on layer bit width. We can take a close look at this problem. When using fast algorithm, the transform here will increase the bit width of the multiplication in the transform domain, so we will have some overhead. For complex number, the ideal complexity 7 is 25%, but if we use 8-bit features and weights here, this saving ratio will be down to only 12%. To know this problem better, we can take a closer look. We observe that conventional rings use ring multiplication for mixing information between components to recover capacity, and use component-wise ReLU for nonlinearity. Then, if we use the fast algorithm, in fact, it is the transforms here and here actually mixing information, and the bit width increased here is actually an extent as a side effect. To resolve this issue, we propose a novel ring algebra. We maximize Howard efficiency by setting the transform matrices to identity for ring multiplication, and this is equivalent to component-wise product or group convolution. More importantly, we propose to recover model capacity by using ring nonlinearity. This is achieved by mixing information through the transform U here and here before and after the component-wise ReLU, and we call it directional ReLU. To further reduce overhead, we prefer to use simple U and V, such as Adama transform H here. Now, I will talk about how we implement our idea of CNN modeling into Accelerator architecture. We consider two sparsity settings, n is 2 and 4, and set the UV matrix to Adama transform. Since we adopt algebraic sparsity, the integration into any existing accelerator architecture is very straightforward, and here we choose IECNN as our backbone because it is optimized for computational imaging. Then we can simply replace convolution engines by ring-based RCON here, and then replace ReLU units by directional ReLU here. And for the ring convolution engine, its microarchitecture is very similar to real value engine. For example, for n equals to 4, we can replace these 32 real value channels by 8 4-tuple channels, and then replace the basic computing unit to ring convolution, and finally replace the component-wise ReLU by directional ReLU. For this directional ReLU unit, we propose to implement it using an under-fly and full-resolution data path. It is to reduce additional memory access and to avoid additional quantization, which causes 0.2 dB of PSNR drop. Now I will show the model and design evaluations. For the model evaluation, we will compare different algebras in terms of image quality and quality efficiency trade-off. For the RingCNN, we will show the layout results and accelerator comparison. For image quality comparison, we compare different ring algebras using 4 different CNN models. They are for 2 applications and 2 performance nodes. And in all of these test cases, the proposed rings here and here show consistent advantages in terms of PSNR. To include area efficiency into the comparison, we synthesize the designs for different ring algebras with 40nm technology. And no matter for n equals to 2 or 4, the proposed ring can show the best image quality and area efficiency. Here we show the layout result of RingCNN on 40nm technology. We implement 2 designs, n equals to 2 and 4, and the power consumption is about 3.7 and 2.2 watts respectively. Now we compare them to layer backbone ECNN. For image quality, the N2 case gives similar or even better PSNR. And for the N4 case, the PSNR is only degraded by 0.1 dB. Here we show the performance comparison in terms of area and power consumption. For the convolutional engines, the original bars here, RingCNN gives near maximum hardware saving ratios, which are very close to n. This advantage is from the proposed ring algebra. Finally, we compare 2 different sparsity approaches. Spartan for natural sparsity, TIE for low-rank sparsity, and RingCNN for full-rank sparsity. We compare them in terms of equivalent efficiency, which is related to hardware efficiency and compression ratio. RingCNN can deliver high efficiency with relatively low compression ratios 2 to 4. This advantage is from our choice of using algebraic sparsity. This is my summary. We investigate the fundamental algebraic sparsity and build a unified framework RingCNN for extensive exploration. We also propose a novel ring variant with directional ReLU, which can achieve near maximum hardware saving and graceful image quality degradation at the same time. Finally, we implement 2 RingCNN accelerators to enable CNN-based computational imaging on edge devices. We show that equivalent 41 TOPS at 2 to 4 watts is possible only using 40nm technology for advanced computational imaging. My presentation ends here. Thank you for your attention.